All right, so it should be recording now. All right, so today what I'm gonna do is that, well, we talked about rotating unbalance in last class. So what I want to do today is I want to go over a couple of examples, hopefully 2 or 3. We'll see how we go with these examples, and I'm also going to show you how to model a rotating unbalanced system, a rotating system with some unbalanced mass in OpenModelica, or in Modelica language, better to say. You're not going to have a project on that to use Modelica to model a rotating unbalanced system, but it's good to know. You can see how easily you can actually make that model in OpenModelica. Very similar to force vibration system, a system under force vibration. All right, we'll get there. Let's go over the first example. So this is an example. Get problem statement there. It says we have a 40 kilogram fan, a 40 kg fan has a rotating unbalance of magnitude 0.1 kgm. And I'll tell you what this kgm is. Kilogram meter. Now the fan is mounted on the beam. The fan is mounted on a, I guess, a cantilever beam. A cantilever beam. That's not how to write that. Lever beam, as shown. Let me draw it here while I'm writing the problem statement. So you can think about it as, oh, that's not the color I wanted. All right, so you can think about it as a cantilever beam like this. Over this way. Oh, it's cantilever, so I'm just going to fix this side. That's a support. Let's emphasize that it's a support. And then we'll have the motor here. Let's say the fan there. How should I show the fan? All right, I guess I can do what I did there. Just put it like this to show that at least to some degree it's a fan. And it's rotating. All right. It says the beam has been specially treated to have, so add that, the beam has been specially treated to add, I believe, viscous damping, to add viscous damping to it. Viscous damping. As the speed of the fan varies, of the fan, or better to say, is varied, it is noted that its maximum steady state amplitude is 20.3 millimeters. Now the question is, what is the fan's steady state amplitude when it operates at 1000 RPM, or let me write it this way, revolution per minute. All right, couple of properties we are given. We know the length of this beam is 1.2 meters. What else do we know? We know the modular elasticity is 200 times 10 to 4 or 10 to 9 Newton per meters. I is 1.3 times 10 to minus 6 M4, and that's pretty much it as far as I see. All right, so we have a 40 kilogram fan, right? We have some structure. We can model that as a cantilever beam. The fan is sitting on the tip of this beam. Now, it's specifically mentioned that this system also has a viscous damping. So some C or damper, we can imagine that they treated this beam, added some material to it to make sure that it has enough damping. Now they vary the speed of the fan while the fan is working, and they realize that its maximum steady state amplitude is 20.3. So this is the maximum steady state amplitude. This is the weight of the fan. And let's take a look at this 0.1 km, kilogram meter. Now what this is it's mentioned that the unbalanced magnitude or rotating unbalance of magnitude, this is the magnitude of rotating unbalance. So looking at the unit, it's kilogram meter. So what we are given here is directly the value of m naught E. M naught being the unbalanced mass and E being the eccentricity, the distance that unbalanced mass has from the axis of rotation. So it's mass times distance. We are given m naught E directly instead of telling us what m naught is and what E is, how far is that from the axis of rotation. We're just given the multiplication value. All right. Now what we're asked to find is that, well, given this information, we know the property of the beam. Given this information, we want to know what is the fan's steady state amplitude when it operates at this 1000 RPM. So let's start with this, let's say, cantilever beam. Right? We said we can always model a cantilever beam as the spring mass system. Right? In this case, we're also given that there is some viscous damping added to it. So I can say, let's assume that this is my system right now. The equivalent of the system I have. That would be M. Maybe in this case, I have a rotating unbalance. So let's do it exactly the way we were doing for a rotating unbalance. This is M naught. The whole structure's mass is M. We have some spring there and some damping there. Call this K, let's say, and C. Or typically cantilever beam, we just replace that with the spring, but in this case, we are specifically said that there is viscous damping. So I put this damper there too. So it's very similar to what we studied when we were talking about rotating unbalance. We just have to identify the correct or right values. Right? This is M, as I said. This is M naught E. And this one is the maximum. I represented with X max. This is the maximum of the amplitude for the steady state response. Remember, we said we have steady state response and transient response. In case of rotating unbalance, which is a type of force vibration, we ignored the transient response. We said, let's just go directly to a steady state response. That's what we care. And we did all the analysis, all the plots we provided and discussions we had over those graphs, how the steady state, how the response changes. Everything was about the steady state response. And in that case, X, remember, was the amplitude of the steady state response. So If you remember from the observations we had or the conclusions I made at the end of that topic, one of the conclusions was that we found what is the maximum amplitude ratio. Remember, amplitude ratio was mx, or in this case, we don't really call it amplitude ratio, we just call it mx over m naught e. We said that one is max when we have 2 zeta square root of 1 minus zeta squared. This is from before. We already know that. Now, x is max. We are given that x is max. The value of the maximum x is 20.3 millimeters. We know m, and we know m naught e. So the only unknown here, we can actually use that because specifically we said this is the maximum steady state amplitude. So this is x max there. For this fraction to be maximum, but m is fixed, m naught e is fixed. The only thing that changes is x. Remember, we represented in this form because we wanted to have a dimensionless or non-dimensional number when we were plotting that response. So in this equation, the only unknown is zeta, is damping ratio. We can actually find zeta from there. M would be 40 times x, 20.3 divided by 1,000. So I think it's going to be 23 over m naught e. The number, the value is directly given, 0.1. It was 0.1, right? Yeah. Is equal to 1 over 2 zeta square root of 1 minus zeta squared. We can actually find this from there. So I think the value for this fraction, I found it already, is 8.12. If I square both sides, let's say 8.12 squared multiplied by 2 zeta. Let me write it this way. 2 zeta. Oh, not 2 zeta. I'm squaring everything, so let me do it right. So 4 zeta squared, 1 minus zeta squared is equal to 1. I squared both sides and just wrote it as an equality. So if you do this calculation, you'll get an equation as in the form of zeta to 4 and zeta squared. Right? I can give you the equation directly instead of going into details of doing the math. But that's what you're going to get. Let me use my notes, make sure that yeah. So you're going to get 263.74 zeta to 4 minus 263.74 zeta, that is zeta squared, and this is zeta squared, zeta 4 is equal to 1. Now this is a polynomial, is a 4th degree polynomial. How are we going to solve this? Right? You might say, well, we actually don't know how to solve 4th degree polynomial, but the fortunate thing is that we only have zeta squared and zeta 4. Right? So what I need to do is that I'll just, let's say I'll take this as, to make it easier to represent, I'll take, or maybe write it here. Take zeta squared as u, right? Change of variables. So that becomes a typical second order, I would say, equation that we usually deal with. Right? It becomes 263.74 u minus 263.74 u squared minus 1 is equal to 0. So this is a 2nd degree polynomial. We can actually solve this. Right? You can find the roots for that. Right? If you find the roots, let's call this, for instance, u1 and U2, 2 roots of that. I got 0.0038, and the other one I got 0.9962. All right, so we have 2 U values, and obviously for each U, we are going to get, let me go to the next page. I'll write it there. So for each U, we're going to get 2 zetas. All right, let's see what we get there. For each U, we're going to get 1 zeta. Let's put it this way. So I'm just going to replace U with zeta squared. So zeta squared 1, zeta squared 2. All right, the first one was 0.0038. Second one was 0.9962. Now, each of them is going to give us 1 zeta, like zeta 1, zeta 2, positive value. So which one do we have to choose? That's the question. Right? How do I decide which zeta value is the correct zeta? Or I should just go with both and say either of them can be zeta. Can anyone remember? How did we actually decide, or how do we decide? All right.
If it's larger than 1 over the square root of 2, then it's too high, and then it can be the correct value.
Exactly. Thank you, Yusuf. Yes. So we said that we only have maximum. In this case, they measure that's the steady state value in the maximum. Right? They said this is the maximum. This is the steady state amplitude, maximum steady state amplitude in this problem statement. Right? So obviously we had some maximum. Now we said we only have a maximum in our curve when we are looking at the amplitude. A maximum occurs only if zeta is greater than 0, is smaller than 1 over the square root of 2. So this one doesn't give you a correct value. We only, let me put it here, maximum value occurs only if zeta is greater than 0, smaller than 1 over square root of 2. That's something we observed in the last class when we were talking about rotating unbalance. So the second one, if you find the square root is out of this range, that's not something we're interested. The first one gives you 0.0617, if I did the math right. So this becomes the damping ratio, zeta. All right, so I got my damping ratio. I'm still far from what I want to find. I'm asked to find the fan's steady state amplitude when it operates at 1000 RPM. All right, so what is the equation to find the amplitude? Right, the amplitude, well, we said m naught mx over m naught e. Remember, this is not at maximum. This is just the general expression for that. Was r squared over square root of 1 minus r squared squared plus 2 zeta r squared. Now I have zeta in this equation. I have to find r. Right? What was r? Well, I need to find x at a given rotating speed. I also need frequency ratio. What was r? R was omega r over omega n. Now omega r is the frequency of the rotating unbalance is given. It's 1000 revolution per minute. Right? That's the frequency I'm interested in, to find what is the amplitude at that frequency. So 1000, well, it's RPM, is a revolution per minute. So I have to convert that to radian per second. How do I do that? I'll say, well, one revolution, think about the circle, is 2 pi times 1 minute is 60 seconds. So what comes out of this would be minute per minute, radian per second. This is radian. So 1000 times 2 pi divided by 60. Hopefully I did it somewhere. I did not do that. So I'll just write it that way. Let's see, 2000 pi divided by 60. That would be radian per second, whatever number that gives. What is omega n? Natural frequency would be square root of k over m. Now what is k? Going back, we have a cantilever beam and we are interested in the deflection at the tip of this beam, this deflection. You want to replace that with a spring. And we know how to go from a beam to spring, right? Hopefully at this point. When we have a cantilever beam, right? Let's write it this way. K is 3ei over L to 3. So we have 3 times 200 times 10 to 9, I believe. I was the cross-section, area moment of inertia, 1.3 times 10 to minus 6. 1.3 times 10 to minus 6 divided by 1.2 to 3. That should give me the value for the stiffness. And that I got as 4.51 10 to 5. Hopefully I got the numbers right. As I always said, you do the calculation, you got a different number, 90% chance, trust your own number, I would say. All right, so omega n from here becomes square root of this value, 4.51 times 10 to 5, divided by mass, which was 40 kilograms. This becomes 40. I hopefully did that math somewhere. Yes, 106.2 rad per second. All right. So now I have omega r and I have omega n. So I can calculate r. All right. So r becomes 2000 pi divided by 60 times 106.2. That I calculate. I have it as 0.986. It doesn't have any units, frequency ratio. All right, so now we can go back to what we were doing here, right? This equation there, I found zeta. Now if I have R from my system, now I can use that to find X. Remember, X is the amplitude of the steady state response. So I can find X from there. I take it here. Now I have everything I need. X would be m naught E over m times R squared, square root of 1 minus R squared squared plus 2 zeta R squared. I know m naught E, I'm given that, is 0.1. M is 40 kilograms. R now I know is 0.986. And zeta also I know it is 0.0617. Plug in these values, you'll get 19.48. I converted that to millimeters directly. The output of this would be in meters, obviously, and then I convert that to millimeters. So knowing properties of the system, that's exactly what you're trying to find. This is the amplitude of the steady state response at 1000 RPM, the speed of the fan. So what we started from, we were given a fan, or we knew where the maximum or what the maximum was. We didn't know where it happened, but we knew what the maximum amplitude of the steady state response was. So we used the information we had from before, that when we were talking about rotating on balance, we knew that mx over m naught e is maximum. Its maximum value is 1 over 2 zeta square root of 1 minus zeta squared. So the only unknown in that equation, we were given everything else was zeta. We could find damping ratio. Now in damping ratio, we have damping ratio. In order to find, remember what was the task? To find the fan's steady state amplitude when it operates at 1000 RPM. We use the general equation. Mx over m naught e, we said, is always equal to r squared, 1 minus r squared plus 2 zeta r squared. Square root of that. We wanted to find x. That gives us x for any given set of parameters, like r, zeta, m naught e. We knew m naught e, we knew m, we knew zeta, we've calculated that. Only missing part was r. To find r frequency ratio, we needed, well, it's a frequency ratio. We needed rotating frequency and natural frequency. Rotating frequency is given. We're looking for amplitude at 1000 RPM. So we just converted that to radian per second to be consistent. Omega n was a natural frequency, or square root of k over m. We needed k, in this case, a cantilever beam, so we could find k. Knowing omega r on omega n, we could find r, and from there we could get x. All right. Any question about this one, guys? All right. So far, so good. Let's take a look at this, the next example. All right. Let's take a look at this one. We have a 60 kilogram, 65 kilogram actually, sewing machine, industrial sewing machine. This one has a rotating unbalance of 0.15 kgm. Again, we are given m naught e directly. Now it says the machine operates at 125 hertz. That's the frequency of the operation for this machine, and is mounted on a foundation of equivalent stiffness, and that stiffness is given as 210 to 6 Newton per meter, and damping ratio of 0.12. Now we're asked to find what is the machine's steady state amplitude. Steady state amplitude. All right. Same story, right? We said for a steady state amplitude, well, we know the general expression is mx over m naught e is r squared over square root of 1 minus r squared squared plus 2 zeta r squared. Let's see what we're given. We know m. We know the unbalance, rotating unbalance together, m naught e. This is the machine the frequency of the machine operation, or the frequency at which the machine operates. I'll talk about it in a minute. Let's go with the equivalent to stiffness. It's obvious this is K, and the damping ratio, we also know it's zeta. Now, what is that 125 hertz from the parameters that we know? Here, R is omega R over omega. What is that 125 hertz? Which one of these parameters is that? I'm going to wait till someone answers.
This is the excitation frequency?
Yeah, that's excitation frequency. Exactly. Thank you, Sif. So when we say machine operates at this frequency, right, we have natural frequency, and this is the frequency of operation. Think about that unbalanced rotating, right? This is the rotation, the velocity of rotational velocity of that unbalanced mass. Think about it. Rotational velocity is the same as frequency, right? They have the same unit. Omega is radian per second when we talk about natural frequency. Remember at the beginning when we were talking about that pendulum, the beginning of the semester? So think about this rotating, unbalanced mass is rotating with this frequency, 125 hertz. All right, so we need omega n, or in this case we have omega r. It's 125 hertz, so we have to convert that to radian per second. I'm just going to write it as 2 pi 125. It's going to be 250 pi radian per second. Omega n would be the natural frequency, k over m. K is 210 to 6, and m is 65. So you'll get your natural frequency as 175.4. If you do this math, you're going to get R as 250 pi over 175.4. And that'll give you 4.48 as no unit. Well, the rest is pretty straightforward, right? When you have R and you have zeta, well, from there you can actually get your X would be m naught E over m R squared over square root of 1 minus R squared squared plus 2 zeta R squared. Here we know m, which is 65. We know m naught E, 0.15. We know R, we found that as 4.48. Same story for R there. And zeta is directly given in the problem statement. If you plug in these values and convert the unit, you're going to get 2.43 millimeters. The output of this equation obviously is meter, but this is going to be the value in millimeters. So that's going to be the steady state. That's what we were looking for. All right, so what does this tell us? It tells us pretty much if the sewing machine operates in that frequency, that's how much the machine is going to oscillate or vibrate. That's the maximum amplitude of the vibration for the machine, going up and down because of this unbalanced mass. Now quickly, let's see how can we actually model a rotating unbalanced system in OpenModelica. So I have it there open. I'll just let's just call it rotating on balance. Hopefully everything is unchecked. I'll go to Modelica, following the same process under mechanics, under translational components. I have too many things open. All right. We need, okay, keep in mind that, before going there, keep in mind that what we are looking at, right? We are looking at the system like this. It's rotating, right? There's a spring and there's a damper there, C and K. This is the M. So what do I need? I'm going to take a spring damper element. I'm just going to call it spring damper. Make it a little bigger. I can rotate that with Control R. So I'll just use Control R a couple times. Upward arrow can be downward or it can be in the horizontal direction. Direction doesn't matter. It's just for the sake of representation. We need a fix support. We'll just call it. I'll just call it floor. We need a mass, obviously. Make sure that use Control R, rotate that, make sure the arrows are lined up. Well, both of them are upward. I'm going to connect them. Left click on this port, move to the next port, let go, and left click again. So they're connected now. Now keep in mind that, remember what was the equation of motion for rotating on balance? It was m x double dot plus cx dot plus kx is equal to, I can do a better job than that. It was mx double dot plus cx dot plus kx is equal to m naught e omega squared sine omega RT. Omega R being the frequency of excitation, m naught e omega squared was basically the amplitude of the excitation. So this is just the force vibration, right? Force vibration. And that's how we solve this equation of motion. If you remember, we said you take that as F naught. So pretty much what you have is mx double dot plus cx dot plus kx is equal to F naught sine omega RT. It's a force vibration. You have a spring mass damper, and this is nothing but a spring mass damper system with some force applied to it. Now, what is that force? That force is F naught sine omega RT. And F naught being the value of F naught, the amplitude, now depends on the frequency with which this unbalanced mass is rotating and the unbalanced mass. How far is that from the center of rotation? M naught E omega squared would be the magnitude of this force applied to the system. And that's why we studied this under force vibration, because it is a type of force vibration. The only difference is that instead of actually having an external force applied to the system, this external force, in this case, or the force that is making the system oscillate, occurs or happens because of this unbalanced mass rotating with some velocity, with some angular velocity, omega r. Right? So that's why we studied this under force vibration. It is force vibration, but instead of having a force outside, we have some kind of an excitation because of rotating unbalance. So we follow the same logic when we are modeling. Right? A spring mass damper, remember how were we modeling the force vibration using Modelica? The same story. Right? I'll go to Modelica blocks and sources, and I say I want a harmonic source, like some sine function. There you go. Here we have sine function. I just drag and drop it here. Let's call it sine input. And I'm gonna move this a little lower there, maybe not too much so we can see that. This is smaller. Rotate it this way. Now, this is the input. As we said, the system needs something to tell or the model needs something to tell the system what is this input. Is it displacement? Is it force? Is it what type of signal you are giving me as an input? Right? To make that happen, right? Close this one. This source is under blocks. Close that. We'll go back to mechanics, translation. We'll go under sources there. Over there, we can determine what we are giving and what is the nature of this input signal. Right? In this case, it's a force. So I drag and drop the force connector. Remember, this is just a connector. Right? It doesn't really do anything. The only thing it does, it tells this model that, well, this signal coming is a force and should be applied, obviously, to this mass. Connecting this, it's connected. Double click on it. There is really not that much. We don't need to check anything there. All right, so let's give the parameters. Spring mass damper. Well, let's go back to the problem we had. Oh, so crazy there. We actually don't have C value. We actually have to calculate that. All right, let me see if I did that. Yes. So I'm going to do it right there. Close this. So for simulation purpose, I'm going to put it here. For simulation purpose. C, I know, is 2 zeta m omega n. I have everything I need. 2 zeta is 0.12. M is 65 kilograms, and omega n, natural frequency, I found it to be, sorry, things are a little messy there. I just don't want to erase that. It was 175.4. We actually found it here. This gives you the value of 2,736.24. All right. So now I have the value for C, 2736.24. Go back there. I can put it here, 2736.24. Stiffness, well, I have it already. It's given 2 times 10 to 6. So 2E6. I can leave the rest empty. We're going to get some warnings, but doesn't affect the way we do the model. The mass, mass for the system was 64 kilograms. So I'll just put it 64 kilograms there. The rest, we can give some initial displacement and velocity if you want. If you don't, I believe it's going to assume that it's 0. So since we're interested in steady state response and the initial conditions only affect the transient response, we can just leave it empty, or we can just give it 0, some number. Again, you get some warnings, but not a big deal. All right, there. Frequency, we had that frequency. We said it's operating at 125 hertz. So I'll just put that directly here, 125 hertz. Unit is hertz here. The amplitude. Now, I said amplitude is F naught, and F naught would be M naught E omega squared. All right. Let me double check. Yeah. F naught E omega squared. So I have to find that. Hopefully I did it somewhere. Let me just do it right here. For purpose of simulation, say what is m naught e omega squared. As a matter of fact, I'm just going to plug it directly. Right? That would be m naught e, we have it, 0.15. And omega, oh, I see. I have to convert that to radian per second. This is 100, this is omega r. Right? So 2 pi times 125 squared. Just make sure that you do that. Omega should be in radian per second whenever you see omega. That one, we just plug in 125 because the unit we could use hertz for that system. This will be 0.15 times 2 pi 125. Actually, I did that calculation. It's 785.4 squared. I'm just going to use this directly there. Now, the amplitude of this, as I said, is m naught e omega squared, and that's 0.15 times omega. We got it as 785.4. I'll just put squared there. I'll let the software do the calculation. And nothing else. Let's save this. On desktop, I'm just going to rotate it, rotating on balance. Let's check the model. I have 25 equations, 25 variables. We should be okay. Let's see how does this work. And let's run this simulation for half a second. I'm going to use more points to get a very smooth graph. Might take some time to run the code, though. So Modelica is going to compile the code, put together all the parameters you need. All right, let me erase this. I don't think I have a way to make it hidden. I guess the only way is just to erase it. No, I do not. All right, so I'm just going to erase that. So we just go directly to from modeling to plotting. If it doesn't go there, you can just click on plotting after it's done. You just have to make sure that it says the simulation is run successfully and get the result. And keep in mind, you have to be on diagram view. If you are on text view, you are going to see the code behind this model. You don't want to see that at the moment. If you want, feel free to take a look how does Modelica language works. Right? This is the language behind the physical model we are making. The software is putting together. Or writing this code for us. Go to diagram view and let's go to plotting and take a look at what we got. Hopefully things are right. So under mass, I'll go for S, which stands for displacement. And I have some, this part is the transient response. Remember that we said we are not talking about transient response, so we can just safely ignore that part. Somewhere here, maybe there is still some effect of transient response. Maybe not even that far, maybe up to here. But then after that, we start seeing the steady state response only. Right? The first part is transient plus steady state. I should always do that. I don't know why sometimes I just put transient. It's a combination of transient and a steady state response at the beginning. And then once after a few seconds that the transient response fades away, we get into the part of the response that is only dominated. The beginning is dominated by steady state response, and at some point, transient response is totally gone, and the response is just a steady state response. Now, if I zoom in a little bit on this, let's zoom in and just clear this. Let's zoom in somewhere there, maybe somewhere here. Now, if you see the value we're getting, it's very close to what we got from our calculation. This is in meters. So what we're getting here is somewhere about 24. Oops, that's not what I wanted to do. Zoom in there. There you go. It's somewhere about 2.44 millimeters. And what we got there, right, if you look back, we got 2.43 millimeters for the oscillation of the mass. So it's pretty close. It's still a little oscillating because we still have some effect of transient response. So you have to run the simulation a little longer to totally eliminate the effect of transient response. But that's how pretty much you can model rotating unbalance in Modelica, right? Just all you need to think about is just basically a force vibration. The amplitude of the force input signal is m naught e omega squared, and that's it. All right. Any question about this one, folks? All right. What time is it? The exam's 45. You know what? Let's just stop here.